Okay, today we're looking at question 6.16, 6.16. It asks us to identify all the prime factors for the number 36. So that's our number we're working with, 36, and it wants us to use a factor tree. So if you don't remember how to do a factor tree, that's the method we are going to use today to identify all of our prime factors. Prime factors are different from factors in the sense that they are the prime numbers that make up every single number. So, 36 has lots of factors, but not all of them are prime. We want to whittle down all of the factors of 36 until we're only left with prime numbers, and the best way to use that is to use a factor tree. So that is what we are going to be working on today. Let me zoom out a little. There we go. Identify all the prime numbers, prime factors for the number 36. Use a factor tree. So to do this, we are going to have 36 at the top, and then we have to think of two numbers that multiply together to make the number 36. So they might have multiple options. There are more than one option for this number, 36. We could do, for instance, 6 times 6, and it's always handy to have our calculator beside us so we can test these theories. 6 times 6 is 36. So I could do 6 and 6, because 6 and 6, when multiplied together, equal 36. Now, if I was so inclined, it might pop into my head that, 18 times 2, oh, look at that. 18 times 2 equals 36. So I could do 18 times 2 equals 36. 18 and 2 are both factors of 36. Now, are they both prime factors? We remember that a prime number can only be divided by itself or 1. Itself or 1. And we can see 2 is in fact a prime number in that way. 2 can only be divided by itself or 1. You can't divide 2 by anything else and end up with a whole number. That's the important part. You need to end up with a whole number. But 18, you can end up, we can do 18 and we can do 1, but we can also do, 9 and 2. We could do 6 and 3. So there's more work to be done here. This isn't a prime number, not yet. Now, 2 is a prime number, so I'm going to take a different color. Let's see if I can get a nice blue going on. And I'm going to circle 2 because it is one of the prime factors for 36, but we want to identify all of the prime factors for 36. So there's more work to do on this 18. So let's go back to black. 18, I like 9 times 2. Let's do 9 times 2. I know that makes 18. I might check it on my calculator just to make sure. 9 times 2. There we go, 18. I might also do 6 times 3. I know that also means 18. That also makes 18. So I could have done either one. Neither would be wrong. You'll see that I ended up with another 2. I know already that that's a prime number, so I'll give it a nice blue circle. And a 9. Now, is there anything that I can divide 9 by that's not itself or 1? Well, I can divide 9 by itself. I can divide 9 by 1. I also know, and you might know if you consulted your multiplication table, that 9 can be broken up into 3 times 3. Okay, so we've got 3, 3, 2, and 2. Let's see if these are prime numbers. So 3 can be divided by itself, for sure. 3 divided by 3 is 1. 3 can be divided by 1. 3 divided by 1 is 3. Can 3 be divided by anything else and get a whole number? Well, nothing's coming to mind, and if I checked my multiplication chart, it would show me that no. 3 can't be divided by anything other than itself and 1, making it a prime number. So, identify all the prime factors for 36. Use a factor tree. The prime factors, and I'll write this in my answer, therefore, my 3 dots meaning therefore, the prime factors for 36 are 3 and 2. There are no other prime factors for 36. And here's the amazing thing. If we did this right, then they should all multiply together to create 36. Let's give it a test. We've got 3 times 3 times 2 times 2 equals 36. So that's how we know we did our factor tree right. All of our circled prime numbers should multiply together to create our number at the top. And this is the amazing thing about prime factors. They show us that all numbers are kind of secretly composed when we whittle them down enough of prime numbers. It's kind of amazing to see. All numbers are composed when we whittle them down of these basic building blocks, prime numbers. So let's do another example, just one more quick one. I'm going to get rid of everything I have here. And let's do all the prime factors for a number like, I don't know, something nice and round. Let's do 100. Okay, 100, we're going to use a factor tree. So we'll have a nice big 100 up at the top. And I want to think of two numbers that multiply together to create 100. Now, if you look to your side, your partner doing the same question might think of two different numbers. For instance, I might do 10 and 10 because 10 times 10 equals 100. But your partner might do 50 and 2. 50 and 2. Let's do both of those just so I can show you that it doesn't actually matter. As long as we're doing our math right, it doesn't matter as long as we are in fact choosing two numbers that do multiply to 100. So 50 times 2, yes, that gives us 100. So that's true so far. And 10 times 10, yes, absolutely, that does give us 100. So let's break these down even further. 2, we know from our previous question, is a prime number. I can give that a nice circle right off the bat. But our numbers here, we've got 50 over here, we've got 10, 10. I know just by looking at them that we can divide these further. For instance, 50 can be divided into 5 and 10. Easy peasy. 5 times 10 equals 50. And we always have to remember, we're not adding these together. For instance, this would be wrong if I did 50 divides into 25 and 25, because those add together to create 50. I want numbers that multiply together to create 50. 5 times 10 equals 50. And over here, to make 10, well, I can divide those into 5 and 2, and 5 and 2. Nice, not bad at all. Now let's look at this one first because I'm seeing something interesting going on. I can see I've got my 2, those are both prime, and 5. Is 5 a prime number? Well, 5 can be divided by 5. 5 can be divided by 1. Can 5 be divided evenly by any number that's not itself or 1? No, it cannot. So that makes it a prime number. So over on this one, when we started with the 10 times 10, we found that the prime factors of the number 100 were 5 and 2. 5, 2, 5, 2. Don't need to repeat them, it's just 5 and 2. Those are the prime factors. Let's see if we arrive at the same spot over here where we started off with 50 and 2 instead of 10 times 10. Well, we've got 5. There we go. That's a prime factor. Because it's 5, it only divides by itself or 1 evenly. We've got 2, another prime number. Here's a 10. I know from over here I can break 10. 10's not easy, or not hard to break down. I can break that into a 5 and a 2. And look at that. We started off with different numbers. Maybe you started off with the 50 times 2, your partner started off with 10 times 10, or maybe the other way around, but you have arrived in the same place because the math is true, so the math's not going to lead you astray. We have 5 and 5 and 2 and 2 on this side. We've got 5 and 2 and 5 and 2 on this side. 2 5s, 2 2s, 2 5s, 2 2s. If I multiply all those together, I should end up with 100. Let's do this side first. It doesn't really matter the order, but it's nice to prove it, and it's nice to feel that symmetry when we have the opportunity. 5 times 5 times 2 times 2 equals 100. We made it. That's our 100 over here. And let's try it in this order. 5 times 2 times 5 times 2. 5 times 2 times 5 times 2, 100. So you can see it doesn't really matter how we begin, as long as we are doing true math. As long as we have two numbers that multiply together to create 100, our factor tree is going to lead us to the same prime factors, no matter what two numbers we start off with. There's multiple ways of getting to 100, but it always leads us down to the same prime factors. So, I want you to give this a try now. See if you can do a factor tree and find the prime factors for a couple large numbers. Good luck.